Okay. Hello, everyone. My name is Garrett Warnell. I work with Peter Stone at the University of Texas at Austin, and I'm also a research scientist for the Army Research Laboratory. We're very pleased to have been invited to give a talk at this workshop on interactive robot learning, and we're excited to share with you some of our recent work. Okay, so I want to start by talking about some things that are going on in machine learning right now. Particularly, there's been a lot of excitement that surrounds learning behaviors from scratch. And we've seen successes in games like domains. So, I mean, like Atari video games or board games like backgammon and Go. And very recently, we've actually seen success in real-time strategy games like StarCraft 2 or Dota 2. And so this is very exciting. You sort of set up your machine learning algorithm, you give it very little prior information, and you let it learn from experience how to be successful in these domains. So as roboticists, one question we have is maybe will these successes that we've seen in these games domains, will they translate to robotics? Will they enable robots to play soccer better? Will they enable sort of robot arms to collaborate more effectively with humans on manufacturing tasks, let's say? And for like a general ground navigating vehicle, will they produce better navigation behaviors? Can we expect things that we've seen in games to translate into robotics? So if we look a little more closely at the literature for the successes in the games domains, we sort of see that maybe there's reason to be concerned. So for some recent results in Atari, we see that in order to train these algorithms to achieve very good performance, they need to process 200 million frames of data corresponding to 10 days of experience time. In the board games domains, for AlphaGo, we saw that for some recent work where they tried to reproduce AlphaGo, they needed 2,000 GPUs and 2 weeks of compute time in order to achieve the same performance as was originally reported. And in the real-time strategy games, even if we have 2 weeks and very specialized hardware, we need to amass 200 years of real-time play in order to learn how to play StarCraft. So if we're thinking about whether or not these algorithms will translate well to robotics, where we have constraints such as we must operate in real time, we need to maybe manually reset some of the robots for episodic tasks, and we get wear and tear on our robots, joints may overheat, ball bearings may fail, right? It seems that maybe these approaches for learning behaviors from scratch probably won't translate to robotics. But I don't think all hope is lost. I think maybe we can take a slightly different approach, and we can learn behaviors from other agents, not necessarily just from scratch. And so the hypothesis we've been pursuing recently at the University of Texas at Austin is that robots will be able to quickly acquire effective behaviors by learning from or interacting with other agents. And by that I mean maybe other trained agents or even humans, other intelligent agents. So we have reason to believe that this might work. In the video games domains, where we saw all the successes in learning from scratch, we also see successes in learning from other agents. So this is some recent work, deep Q learning from demonstrations, where it was shown that if you can acquire demonstration information for playing some of these Atari games, you can do even better than learning from scratch. So that's a really nice result that gives us some hope. I think what gives us even more hope is really that the most autonomous agents we have right now, mainly humans, the most successful ones, they don't learn from scratch at all. In fact, humans learn from other agents such as parents. They learn from educational instructors, maybe at a university, and for even specialized tasks, they learn from coaches. Maybe if you're learning to play soccer, there's someone very, very specialized there who already knows how to play the game and can give you very specific instructions and help you learn. So in this talk, I'm going to focus on learning from demonstration as a means of inter-agent interaction and learning. And in particular, I'm going to talk about two recent efforts that we've had at the University of Texas at Austin. The first is a hierarchical approach to learning from demonstration that has enabled more robust robot navigation. And this is kind of hot off the presses. What we're doing here is we're using teleoperation data of a robot navigating the small ground robot. And we're going to use that teleoperation data, which was provided by a human, to make the navigation behavior exhibited by this robot more robust. In the second part of the talk, I'll talk about a recent observational extension of the learning from demonstration paradigm that allows us to do learning from demonstration even when we don't have sort of hard to acquire demonstration data. You know, maybe you can't collect teleoperations or kinesthetic demonstrations of a behavior. And instead, we'd really like to enable learning new behaviors from just video observations that are sort of freely available online. So I'll dive now into the first part of the talk, which is on learning from demonstration for robot navigation. This is joint work that's led by Shui-Su Xiao and Bo Liu in the Learning Agents Research Group at the University of Texas, and also with my colleague, Jonathan Fink at the University of Austin, or at the Army Research Laboratory. So our motivation here is that deploying an autonomous navigation system for a new environment is not always as straightforward as it may seem. So I'll try to illustrate this by example. So let's say someone sends you a robot, maybe your friend, they send you a robot to use, then this robot can autonomously navigate. But they've tuned it for some outdoor environment, maybe it's got buildings, maybe it's urban. They've tuned that navigation system so that the robot can navigate autonomously in that environment. But they've sent it to you, and you'd like to use it in maybe an office building. This is a picture of the computer science building at the University of Texas. And so I think what you'll find is if you are given such a robot that's tuned for one environment and you try to deploy it in another environment, and you try to supply waypoints to the robot and you expect it to navigate to these waypoints autonomously, you'll find that it doesn't work. But that's okay. Everyone sort of understands this if you've been working in robot navigation, and there's actually a guide out there. So if you're using ROS, as many of us do, and you're using sort of the vanilla move-based architecture for doing autonomous navigation, there's actually this very nice document called the ROS Navigation Tuning Guide. So not to worry, let's just consult this guide and we can get our robot to navigate. But if we look closely at the abstract there, we'll see some interesting statements. So they say maximizing the performance of this navigation stack requires some fine tuning of parameters. And this is not as simple as it looks. One who is sophomoric about the concepts and reasoning may try things randomly and wastes a lot of time. So that sounds pretty intimidating, especially if you're not a roboticist. If you just want to use the robot, if you don't have the training to understand the thing. I mean, you may be someone who has invented an autonomous navigation algorithm, but even if you are, and even if you would understand what's in this document, we'll also notice that you will have 23 pages of instructions to sift through. So it's not the tuning procedure we have right now, it's not accessible to people who aren't roboticists. And even if we are roboticists, we may find it very frustrating in order to go work through this guide and get our robot to navigate. So we're inspired in this work that we can do better. And particularly we're inspired by the fact that humans can do this effortlessly. So this is one of our collaborators, Bo, who was one of the lead authors on this work. And Bo can grab an Xbox controller and teleoperate the robot around an environment that might be challenging for an untuned navigation system. He can do this effortlessly, basically on his first try. And so these are the type of demonstrations that we will be collecting in this work. And I'm going to describe to you sort of our approach for trying to tune the navigation stack based on these demonstrations. So the central question we have is, can we squeeze more robust performance out of our existing navigation systems using learning from demonstration and limited human interaction? So that human interaction I'm talking about here, it's a demonstration. And we are particularly concerned with doing this for existing navigation systems. So we're not really interested in inventing an entirely new navigation system. We're instead sort of interested in augmenting our existing systems with a machine learning component. So as an example of such a navigation system, let's just take this ROS move-based navigation stack. This is sort of the vanilla autonomous navigation system that you might use if someone said, hey, get this robot navigating autonomously by tomorrow. And what we're interested in doing is not changing this navigation stack. We'd still like to use it, but we'd like to insert a new component that sort of interacts with this navigation stack, and a component that we would train from learning from demonstration. So the question is, can we devise such a component, and can it lead to better performance out of the navigation system overall? So of course, using learning from demonstration in robotics is not a new task, and even using it to help improve robot navigation is not a new task. Of course, there's a rich body of literature in general. You can go see the survey by Brenna Argall and her collaborators from several years ago if you're interested in that kind of work. With respect to navigation in particular, we've seen approaches even very recently that sort of approach the problem in an end-to-end fashion, where we're trying to map sensor data directly to motor commands, which sort of short circuits existing navigation systems that are out there today. We've also seen approaches that sort of try to approach this problem by picking out specific components of autonomous navigation and applying machine learning there. There's some work that where inverse reinforcement learning was used to process some demonstrations and try to learn better cost maps for navigation. And even in the realm of sort of using a system and wrapping machine learning around it, we have seen some approaches that have a similar flavor to what we're going to present, but they're specific to a certain navigation system. Whereas the approach that I'm going to talk about here, we're sort of agnostic to whatever navigation system you have running on your robot. So what we propose to do here is use behavioral cloning to tune any navigation stack. So for the purposes of this talk, let's pretend your navigation system is described by some function G, which processes sensor data and outputs motor commands. And there's this other parameter for G, which is theta, which we will call the tuning parameters. And these aren't parameters like in the neural net sense of parameters. They're not like weights for linear functions and things like that. They're rather sort of the hyperparameters of whatever navigation stack you have. So for a very common navigation system called DWA that we use in our system for one of our experiments, these parameters are things like how many samples should we take in each component of the motor command dimensions, what's the maximum velocity we'll allow for the robot. So these are sort of parameters that are hard to sort of put real nice equations behind, but they are very important for the performance of the system. And like I said, we're going to use behavioral cloning to learn parameters, learn this data from a demonstration using supervised learning. And so just briefly, like this is sort of the classic supervised learning problem. We're going to seek some theta star that minimizes a cost function that's typical for supervised learning, where we would like to minimize the distance between sort of xi ui, which the demonstrator showed us for some demonstration state. The demonstrator requested some motor commands u, and we would like our function g with whatever theta we're using to produce very similar motor commands to what the demonstrator showed us. So the rough procedure I'm describing is this. First, collect a demonstration. So grab your robot, turn it on, grab your Xbox controller, and drive the robot around. And while you're doing that, record the sensor data that the robot is perceiving, and then also record the motor commands that the human demonstrator asked for via the controller, and call that some data set D, which consists of these XU pairs. And then use a black box optimization algorithm to solve for the navigation stack parameters. So in our work, we use the CMA-ES black box navigation or black box optimization system, but in general, you could use any black box optimization algorithm that you'd like. You provide the data set, the XU pairs, you provide access to G. You don't really understand, you can't get a derivative with respect to G, but you can definitely query it with samples. And then after running this procedure for some time, what comes out to you is sort of the best data in the sense that I described before in the behavioral cloning sense. Okay, this procedure is fine, but there's actually a problem with it. The problem is that humans actually exhibit very different navigation behaviors in different environments. And so, whereas before we were thinking we could get away with just learning a single theta star, when we're faced with environments that exhibit a lot of differences, such as the environment I'm showing here, where we have maybe 4 different kinds of environments. The first being, we called it the curve environment. The second, the obstacle course environment in green. In yellow, sort of a corridor, a curving corridor, and then in red, sort of open space. Each of these is sort of qualitatively different, and what we notice is that humans actually drive differently based on where the robot is. And so we can't achieve what we'd like to achieve with just learning a single theta star because of this. Instead, what we'd like to do is learn a separate theta star for each of those different environments. So the approach we propose, we call it APPLE-D. It stands for Adaptive Planner Parameter Learning from Demonstration. And if we start from the previous steps that I showed before, we will still be collecting a demonstration. We will still be using a black box optimization algorithm in the same way that I proposed. But after we collect the demonstration, what we'll do is we'll perform automatic demonstration segmentation. And this is where we try to automatically discover, using a change point detection algorithm, we used one called CHAMP in our work, where are those qualitatively different environments in the demonstration, and then segment the demonstration based on those change points. And then use the black box optimization scheme I described before, but now do it per segment that you found in step 2. And then finally, so that we know what theta to use at deployment, we also we introduce a context predictor, which is a supervised learning procedure that we use to map the sensor data to the context. So once we know what context we're in based on the sensor data, then we can go grab the correct theta star for the context we predicted. So when we go to deploy this system, we still use the same move-based stack that we had before. Of course, you could use any other stack as long as it can be queried by a black box optimization algorithm. And we insert into that the component that I was describing at the beginning of this section, where we pass in real time, we read the sensor data X, we predict the context using this function B, and then the function M here will just map the predicted context to the theta star that we learned using black box optimization. And we do all this in real time. So X will be read at some frequency, and new thetas will be supplied to the navigation stack while the robot is navigating. And that's what allows us to detect context on the fly and retune the navigation stack on the fly. So we did some experiments. What we used was a robot. We used a ClearPath Jackal, and the sensor input was LiDAR returns from a Velodyne Puck LiDAR. Of course, we had our human demonstrator, who was our one of the lead authors here, Bo, and he had an Xbox wireless controller and supplied demonstrations of the robot navigating in the way that he would do it. And then, of course, we constructed a challenging sort of obstacle course environment with these qualitatively different sections to it so that we could investigate the efficacy of AppleD. So what I'll show now is a video of just how the vanilla move base performs without any AppleD augmentation using the parameters, the navigation stack parameters that ClearPath, the robot manufacturer, suggests that you use. And so this is the robot trying to navigate this curved corridor, and it's not streaming issues that is causing the video to freeze. It's actually the robot slowing down, stopping, trying to recompute. And you can see when it fails, it fails to find a navigation solution, and it enters a recovery behavior, which here is to just back up a little bit blindly. And so every time it does that, of course, we grab the controller and try to move the robot into a better position in order to not have it knock over our cardboard walls. But you can see the vanilla navigation system is not doing very well in this environment. And this is exactly the problem I was describing before, which is that if you don't have a nicely tuned navigation stack, then autonomous navigation is not going to go great for you. So here's a little bit longer version of the demonstration collection that we had. So Bo grabbed the controller and he teleoperated the robot around the environment while we were recording the sensor measurements and the requested actions. And of course, you can see that he has none of the problems that the robot was having. I mean, I know you can only see the antenna of the robot right now, but obviously Bo is able to very quickly and easily drive the robot through the corridor. And then you can see also when he hits the open space, he speeds up the robot to try to get all the way across the space as fast as possible, which is another qualitative shift in the human's behavior. So what I'll show you now is sort of how AppleD worked in this environment at deployment time. We have the same context that I described before. We went through the procedure that I described. We segmented the demonstration. We did the behavioral cloning black box optimization procedure for each of those contexts. And we learned a theta star for each of those contexts. And then we also had a context predictor that we used at deployment. What you'll see in the video is the top half is going to be the vanilla move base algorithm that running that I showed a few slides ago. And then on the bottom is going to be the system that's running using our proposed approach, AppleD. So you can see the robot has a lot of problems with the first context when in the vanilla move base type of framework, but powers right through it using the tuned parameters from AppleD, makes it through the obstacle course, no problem, sort of in both cases. Of course, when we get to the corridor, this is what we saw before, and you can see now that the system is detecting a new context, applying a new set of parameters to the navigation stack that enables the robot to slowly but successfully navigate through this corridor in a similar way to what Bo showed it to do. And then you'll see right here, it hits the open space, detects the open space context, and raises the maximum velocity for the navigation stack and navigates in a very similar way to the human demonstrator. So just some numbers to go with these plots. So what we've done here is we've segmented each of the contexts individually to look at them separately. So A is there's 4 different rows here, and each one corresponds to a different context. And it's not really important to analyze every every single number in detail, but what you will see is that in terms of real world time to make it through that part of the environment, the Appled approach does it the fastest, which, there's no failures and it's actually moving very quickly. And one thing that's really interesting to note is that once we've tuned it, we actually get the power that you would expect out of an autonomous system, like a computer-driven system, which is that it actually navigates these environments faster than the human demonstrator could. So we found that very, very interesting that, once you tune the navigation stack, it can actually do better than the human when you go to deploy it. Finally, we'll show a little bit of generalization. What we did was we reconstructed the environment. We try to shift we have the same qualitative types of environments here, but we reconstructed them and tried to shift them around the gym a little bit. Of course, we're not going to get it perfect. We're setting up these cardboard boxes, and there's going to be small errors in sort of what we did. The obstacle course isn't exactly laid out the same, but we're still interested in knowing if the training from the first demonstration would lead to good deployment in this environment as well. And so I'll just show you a little clip here. So here, it has again detected that this is the curving corridor context, and then exhibits the behavior that we saw before in the training environment. And then actually it's going to hit the obstacle course here. And this obstacle course is much harder because it sort of has to bend around and do a little bit of slaloming as it goes. And it actually goes, Appled leads to navigation behaviors that are quite a bit faster than the demonstrator gave for that context originally. And then of course, in the open space, it acts like before. So we have evidence to believe that it generalizes at least a little bit. And then if you can keep providing it demonstrations, it will generalize more and more as it sees more and more context. Now, remember, we also wanted to make sure that this was going to be an approach that could work for any robot with whatever navigation stack you have. This Appled framework that we're describing would help you tune whatever robot you have. And so we also have some other robots at UT. We have these BWI robots, which are on Segway bases, and they also run the move-based stack, but they use a different planner at the local level. They use one called the E-band planner as opposed to the DWA planner. So it's a different navigation system that actually has different parameters that are also hard to understand and tune. And what you're going to see in this video, of course, is on the left. We would like this robot to just go down the middle of the corridor straight. If you use sort of the default parameters provided by the E-band designers, you'll get this oscillatory behavior you see in red on the left. When we've tuned it as roboticists who sit with these robots every day trying to get a better behavior, we can reduce some of that oscillatory behavior. But then on the right, we're going to see that we've actually completely eliminated it once we provided the robot a demonstration and used the Appled framework. And so just a brief clip showing it running on another robot using another navigation stack and also in a different environment. Okay, so that sort of concludes the first part of the talk where we're talking about using learning from demonstration to help with robot navigation. I'll now move on and briefly touch upon some of our work we've done in extending learning from demonstration to be able to process observational data like videos. So this is work that has been led by Faraz Tarabi. He's a member of the Learning Agents Research Group at UT. And we have several publications on the topic that you can find. What we'd like to do here, like I said, is sort of enable the behavior you're seeing on the screen where a small child is watching a video and there are some characters in the video that are exhibiting certain behaviors, and the child, just from watching this video, has learned to mimic the exact sequence of actions that was happening on the screen. And so that's the same type of thing that we'd like our robots to be able to do, is process demonstration information of this form. So our motivation here is that control signals are not always available for learning from demonstration. So what I just talked about was great. We had an Xbox controller. We were able to collect a teleoperated demonstration of robot navigation, but there's a couple of reasons maybe that this is not always going to be the case. So the first is you might have a platform which is not so advanced as that ClearPath Jackal. Maybe you have a very old vehicle. Maybe it doesn't even have drive-by-wire in it. It's just not equipped to record control signals. On the other hand, it's really easy now to just like slap a GoPro on the front of a vehicle and collect video data. Another reason might be that you have some pre-recorded demonstration data that was made for humans. For instance, if you're trying to learn how to dance, I think you'd have to study this for a very long time, but this is something you can find on the internet and you can use, and it was designed for humans, and if we want to be able to use it on robots, we need to enable this style of imitation learning from processing just video. So we're inspired here by the fact that deep learning recently has enabled pretty impressive processing of raw observational data. So if we go back to some of the video game domains that I talked about earlier in the talk, like Atari, where they're processing state information as the pixel information on the screen with no extra hand tuning of feature extraction and so on. They've done this by inserting convolutional layers into a gigantic neural network. And what we find is that actually the performance is very good once you do this. This enables you to process this raw observational data and perform very well. So this is just a figure from the Rainbow DQN paper showing that when you have a network like this, you can outperform humans on these Atari games by quite a bit. And this suggests that we can be successful in processing this raw data using sort of convolutional neural networks and deep neural networks in general. So the central question we've been asking here is, can existing imitation learning techniques be extended to leverage state-only demonstrations? So whereas before in the previous part of the talk, our demonstration consisted of states and actions. In the previous part, I had X's and U's to sort of match more of the controls literature, but here it's S's and A's. They're very similar. You can think of them the same way. And instead of getting the action information A, instead we are not given the action information. We don't know. We just have a demonstration that comes in the form of a state-only trajectory. And in this work in particular, we've been focusing a lot on sort of simulated robots of this kind. So this is very standard benchmark domains in the community where we have these limbed robots where we're trying to control joint torques on them to get them to perform sort of very simple behaviors. And even this is very challenging. Of course, we do have plans and ongoing work trying to implement what we've been doing in simulation on real robots to really show the power of these techniques. But the results I'll discuss here have been proved out in these simulation domains. So there's some related work, of course, on trying to do imitation learning on sort of raw state-only demonstrations. One sort of thread of work that's a little bit older is people approach this from the perception perspective, where they sort of try to handcraft ways around this processing raw state information. Maybe they design sort of very complicated systems to remove video from the entire pipeline, or maybe they've designed sort of very specific vision techniques to extract the better features to use for imitation learning. In sort of if you look at it from the controls perspective, from the policy learning perspective, people have been proposed several approaches, like doing sort of handcrafted reward engineering to try to get around the problem that action information is missing, or learning models. One of our approaches is also a model learning technique, and there is lots of work going on in this space currently. So we've had sort of, our contributions have sort of come in sort of two main avenues. The first is some work we've done called behavioral cloning from observation, an ICRA paper from a couple years ago, where it is a very model-based approach to solving this imitation from observation problem. In particular, we learn a model to infer action information from state sequences using experience gathered on the imitator before learning begins. And so I would encourage you to go read the paper if you're interested in this. I'm not going to focus on that in this talk today for time reasons. I'm instead going to focus on our work, our adversarial imitation from observation work, where we are using, instead of doing a model learning approach, we're going to try to leverage the power of generative adversarial networks, obviously a very hot topic in machine learning now, in order to enable this imitation from observation behavior. And so broadly, we have discriminator that tries to determine whether or not the demonstrated behavior is coming from the imitator or the demonstrator. And I'll get a little bit more into that now. So yeah, this is sort of what the system diagram looks like. We have an imitator, that's the learner. We're trying to learn the imitation policy. And then we have a discriminator, which is trying to differentiate between the imitator's behavior and the demonstrated behavior. So the demonstrator block in this diagram is the state-only transitions that you have gathered from this is imitation learning, so someone has demonstrated for you the behavior. And then the imitator is a policy that you're evolving. And as you continue to learn, you can generate behavior with that policy by interacting with the environment. And then that behavior and the demonstrator's behavior are both fed to a discriminator, where the discriminator's job is to try to tell what agent produced which behavior. So we tell the discriminator that the demonstrator produced this state trajectory and the imitator produced this other state trajectory, and now try to tell them apart, right? So the specific data we provide are these state next state sequences. These are available. Action information is not available, but state next state sequences are. And we have this policy pi that we're trying to learn, that's the imitator. And the discriminator is outputting the score function V, which is supposed to be large for, draw it closer to 1 for the demonstrator and push it closer to 0 for the imitator. Like I said before, like our hope for this work is that deep neural networks will help us with this problem. And so, we have been using deep neural networks for both the imitation policy and for the discriminator itself. And so we're very interested to see how this approach would do. And again, this is sort of the graphical diagram of what's going on here, where you have on the right side what the imitator does, the policy pi is in green, and on the left side, just what the discriminator sees for the demonstrator. And you can see we try to pull the V up to 1 for the demonstrator's trajectories and the V down to 0 for the imitator. And then importantly, the V is used, the score is used as the reward for the imitator update. So the discriminator's job is to tell the two behaviors apart. The imitator's job is to then try to modify its behavior such that it can fool the discriminator. And so if you keep doing this in an iterative fashion, that's our adversarial imitation from observation approach. So I'll talk a little bit about I'll give a qualitative example of some of the results. So this is a video we recorded of an expert. So we trained an expert agent in this domain using reinforcement learning in a lot of time. And then we were able to collect this visual demonstration from the simulator. And then we provide that to our algorithm, this adversarial imitation from observation approach. And so this is how the policy evolves over time. So at first, we don't get great behavior, but we're still training our networks. As we make it more and more through the training procedure, we see that the imitator is getting closer and closer to what the demonstration looks like. And then in the end, you can see that the learn policy is basically indistinguishable from the demonstrated policy. And you can see that this is all done using just a visual demonstration, no action information. So it seems that deep neural networks can indeed help enable this kind of learning. So that wraps up the observational extension of LFD that we've been working on at UT and at our Bing Research Lab. I think I can leave you now with maybe some teasers of other things we have going on in the lab. So like I mentioned, we have been extending some of that imitation from observation work to real robot arms. Here's some early videos of some of the successful learning that we've had where this is a pouring task using a UR5 robot arm. We've also been sort of considering the same problem when the demonstrating agent, the other agent is actually an agent that was trained in simulation. And we look at trying to transfer that behavior to agents in the real world. And we've been looking at the sim to real transfer problem on these soccer playing now robots. And then we also have some other work that's sort of very much in the interactive learning paradigm based on the tamer work, learning from human feedback. This is still in sort of high dimensional simulators, though we do have plans to try to deploy it on some robots once this learning from demonstration work yields some good behaviors. So on behalf of Peter and myself, thanks very much again for inviting us to give a talk, and feel free to contact us with any questions, or the students who are involved in doing much of the work. And I'm sorry I can't be there for the question and answer period. My wife is giving birth exactly during the workshop. So Peter has agreed to be online for the question and answer period, and I think he'll be happy to take your questions. Thank you.